you all for those of you in the room and those of you online. Today is our second installment of this semester of the human performance focus area, and we have Professor Marco Santello in from the School of Engineering, and he's going to give us a talk today. Thank you very much. Let me take it away.
Thank you, Jason. Great to be here and give this talk. So, as I mentioned earlier, my lab works on a number of problems that all share one thing in common: understanding mechanism responsible for controlling movement. And as you all know, controlling movement is actually more complicated when you try to break down the rules and the mechanisms than it looks on the surface. So there's a lot about perception. There's a lot about integrating sensory feedback with decision making, controlling movement, and adapting and learning. And so basically, when you start to talk about motor control and biomechanics, then inevitably, at least for my lab, we kind of have two kind of tracks. One that looks at the fundamental mechanisms, and one that tries to push as hard as possible, as effectively as possible, translational work. So you will see some examples here. And so today the topic is really about this intriguing problem that we started to work on last few years on how do human subjects physically interact with each other. And I'm trying to convince you that it's actually very intellectually, conceptually, very interesting problem, but also has some very practical applications also to the clinic. So I'm going to introduce you a little bit about some fundamentals of sensorimotor control. Then I'm going to tell you a little bit about this symbiotic relationship between neuroscience and robotics. Then I'm going to zoom in into this human-human physical interaction topic. Then move to human-machine interaction and show you how learning about how two human subjects work with each other actually has some implications for designing machines that work with humans. And then some application, very, very quick, very simple examples of how you could adapt these machines to the workplace and the clinic. And then I'm going to start with some open questions. All right. So sensorimotor control. And before I move on, if you could give me a sign when I have 5 minutes left, so that I can speed up. At least 45 minutes, right? Yeah. So the reason why I've always been interested in motor control is that it's almost it's an incredible opportunity to really get deep into understanding a lot of different disciplines that come together to truly explain how we control movement, right? And so, first of all, our ability to move in the environment is the net result of interacting between a physical plant, if you want to call it that way in engineering terms, a physical body. But there's a lot of underlying the control, which is the brain, the nervous system in general, that you cannot really see, but you see it in action, right? And you can measure it in a number of different ways. But truly, what fascinates me is truly that if you only focus on biomechanics, you get to understand part of the problem. If you only focus on the neural mechanism, you only understand part of the problem. But to truly get deeper and deeper in understanding sensorimotor control, you really need to understand how the two interact with each other. That's what I see the fun part of this work is. And so another thing that really got my attention during my PhD is that, in fact, if you think about it, when you control your movement, it's always a game of predicting and reacting constantly. So when you move your body in space, you're predicting how that environment will react to your action, but you also sense whether your prediction is correct or not. And you're constantly updating these predictions. And of course, if you look at an infant learning how to walk or to reach for an object, you will see that the infant failed most of the time because still hasn't understood or learned implicitly gravity, the dynamics of his body. His body is changing very rapidly. So if you have this kind of continuous loop of the nervous system evolving, trying to catch up with the body changing, and so on and so forth, right? And of course, as adults, we have a much better way to predict the effects of our movement, our motor commands onto how the body will react and how we react to the environment. And so that's what the research in motor control really addresses. That is the mechanism that enables biological organisms, not just humans, to regulate sensorimotor interaction with the environment. So just to give you a quick overview, you can look at this, as I mentioned earlier, through different lenses of the machinery, so to speak, so biomechanics, and or the controller aspect of it. That is, how the different parts of the nervous system enable moving in the environment. You can look at the neurophysiology aspect of it. So for example, myself and many others, of course, could measure the electrical activity of muscles through electromyography as a window into the understanding what the brain is telling the muscles to do. Or you can look at the highest level of the control system, and you know, could think about brain-machine interfaces as one of the most recent, probably most sophisticated ways of reading out the signals that come out of the brain. And in the case of, for example, someone who might be paralyzed from the neck down, then you could then read the signals, decode them somehow. There are multiple ways of doing it, and then operate on the body or a machine, right? And of course, the clinical implications don't stop at the brain-machine interfaces, but you could also think about prosthetics, right? So it could be part of your body is missing. So now the key for people that work in motor control is to design, test, and validate tools that can kind of, you know, be integrated with your body, not just physically, but also from the neural perspective. That's to become an extension of your body, right? And then of course, this shows the lower limb, this shows an upper limb, and clearly each one of these approaches presented some challenges, but you get the picture of what the field of motor control kind of branches out to. All right, now more onto the theory, so to speak. So as I mentioned earlier, there is always this interplay between predicting and reacting. Every time you move, you create some kind of consequences in the environment or your own body. And the theory, actually the neurophysiology of this is that clearly we're endowed with sensory feedback. So we could sense the environment through vision, through touch, through proprioception. And then the job of the nervous system is to integrate this streams of information. In most cases, this information arrives slightly asynchronously because they have different delays from the time the feedback starts at the periphery. Nevertheless, the brain is charged with making sense of all these different streams of information, use it, and then make a decision about what to do next, okay? And so the idea is that if you only had reaction or sensory feedback driven control, you will always be behind, right? Because by the time an event happens, it might take several tens of milliseconds before the spinal cord and or even later, the brain realizes that something has happened. So you wouldn't be able to move. At every step you fall, you wouldn't be able to judge if the object you just grasped is too heavy or too light or whatever. So then from a conceptual standpoint, you need something else besides reactive mechanism. And that is where this forward model comes in, which has been proposed by a number of authors, in particular Wolper, one of the leading figures in motor control and neuroscience. Basically say, well, look, for sure, you have this box at the bottom here, where you have your body in the environment. And if you follow this arrow, as you plan a motor command, this motor command will generate a movement, which in turn will generate some sensory feedback, which I call actual sensory feedback, and execution, of course. At the same time, and again, this is more theoretical than experimentally supported at this point, but we know that, for example, from research on eye movements, that you have something called a corollary discharge, or an efference copy, which is a copy of your motor commands that you send to your muscles. And the role of this copy is to predict what the consequences of those motor commands will be from a sensory perspective. And this is when now you have something called predictive sensory feedback. Now, the whole mechanism here works if you can compare the predicted with the actual sensory feedback. If they match one-to-one, if the object lifts exactly when you expect it to be lifted, or if the ground, if you feel that the ground is hard, but you expect it to be when you strike the ground with your heel, there is no real perception associated with it because everything is basically exactly you predicted. But if the typical example of the milk carton, that if it's lighter than what you thought, it's gonna fly, all of a sudden you realize something is wrong, and now you gotta adapt your motor commands on the fly. Very simple example, but the general idea is that you constantly have these two mechanisms of predicting and reacting kind of constantly intertwined. So now I would like to switch. I'm going to pick up on the model in a few slides, but now I'd like to move on to so first of all, before I move on, this is a good example of theoretical or computational neuroscience, okay? Where some of these things might not be measurable directly, these are. And so you cannot have you have to design experiments to kind of prove or validate or confirm that this mechanism is truly at play. So neuroscience and robotics in the last, I'd say 20, 30 years have borrowed from each other tools, techniques, analysis to truly advance each other's kind of missions. And some of the outcomes have been in the field of rehabilitation of sensorimotor function, assistive devices, and human-machine interaction, which is one of the key topics I'm going to focus on. So from robotic to neuroscience, so these are some examples. The list is too long to put in one slide, but just some example of how neuroscientists are using robotic devices to interrogate the nervous system. So this device is called KinArm. We have a couple of these in the lab. You grasp the handles, you can move bimanually or unimanually against the force field. The position of the handle, which is your hand in space, you see it on a reflecting mirror. There's a monitor on top of the mirror. And so you can basically act in this environment, and then you can create force fields. So you can create perturbations, or you could test, as shown in the bottom, the ability to perceive where your hand is in space. Okay, and you could test, of course, patients that are affected by pathologies, etc., to really measure very, very precisely the acuity of their perceptual system. So one of the things, as you can imagine, that is an advantage when you use robotic devices is that you have very accurate, very quantifiable information that you might not have if you have a physical therapist trying to gauge, for example, the stiffness of the limb, right? Not to say that that is not done in daily practice or that is bad. It's just that often when you try to compare what happened a week ago and today with the patient, with the device like this, you actually measure the stiffness, you actually measure the position. If you do it by hand, there is some element of subjectivity that prevents a one-to-one comparison, say, of the efficacy of an intervention, okay? This is another example from my lab. So now you could have this kind of big kind of robotic devices. So you could have smaller ones. These are called phantoms. They come in 3 sizes. We use them mainly to study grasping. And so why would you use this in the lab? Because if I ask you to learn how to grasp an object and manipulate it, it's going to take you 1 or 2 tries because you're so used to, again, gravity and friction and all these kind of things that I cannot really study adaptation and learning with a physical object. However, you could create a virtual reality environment. So what the subject sees here is something on the screen. And then you can create force fields similar to what you create here, just on a smaller workspace. And then I could mount a 3D printed object. I have sensors here, probably can see them here. And then in this task, then showing you on the right, the task was to move from this spot to this end zone. But then at random points here, you have to go through this green circle. But as soon as you approach the green circle, the robot kind of perturbs your hand. And so you have to learn, as you keep doing this over and over and over, to anticipate not only when, but also the magnitude of the perturbation so you can go straight. And then you can measure kind of different conditions, and this is kind of an example of the adaptation protocol. So besides neuroscientists borrowing from robotics, there's also been the other kind of flow of borrowing, so to speak, from neuroscience to robotics. And this is an example. Of course, I have to put my study from last century as an example. You will see why in a moment. Not just to market my work, which is now old, but to show that actually this is a good example of how something which was grounded in pure, basic science actually ended up being used for the clinic. So in this work, we asked subjects to imagine grasping objects of different shapes. We used a cyber glove, which at that time was a gaming glove, but my postdoc advisor used it to measure joint angles, and he did his own kind of magic. He calibrated it, and so we could get fairly accurate estimates of hand shape. These are renderings of the hand shapes used to imagine different objects. And then once you have the joint angles for each digit, then you could do this cross correlation matrix. And what you see in each of these acronyms is a different joint. So T is thumb, index, middle, ring, and little metacarpal, the proximal interphalangeal for each digit, and abduction angles. Without getting into the details, you can see that some pairs of joint angles are highly correlated, linearly correlated. Others, like the thumb and other fingers, are not. Which again, just at a glance, you know that the thumb is a little more independent as you grasp different objects or imagine to grasp different objects. And not so much for other adjacent fingers, but they tend to go together. If you apply principal component analysis, which basically extracts common features across the large data set, what we find is that two principal components could account for over 70% of the variance. If you apply three principal components, you can contract up to 90% of the variance. So what we learned from this is that even though subjects were asked to grasp, imagined to grasp 57 different objects, different sizes, different shapes, there are three fundamental patterns that I can use to reconstruct each of those hints, shapes, with a very high degree of accuracy. Now this, unbeknownst to me, was then used a few years later, I'd say probably 8-10 years later, by a different robotics group, one at Columbia, one at Harvard. But basically they borrowed this idea to say, look, instead of planning robotic hands, joint by joint, this is done traditionally, what if we bind all of these joints into principal components? So why don't we send three signals that describe the relationship between joints rather than the body of each joint? So this shows an example from Peter Allen at Columbia University doing a grasp planner using a software called GraspIt. This is the group by Asada, where they actually build physical hands that could actually use this principal component. So this is awesome, right? But then I was doing my sabbatical in Italy at the University of Pisa and talking with Antonio Bicchi, who's a very well-known roboticist. We came up with the idea of not only do a robotic hand, which he did, but also use that for the prosthetic hand. So that kind of triggered a number of incredibly good things, including bringing Mayo Clinic, Minnesota as a partner in this collaboration, and then getting some funding from NIH, first an UP21 and the current R1 clinical trial grant. But the idea was, can we actually validate and test whether this prosthetic hand that uses one principal component, just open and close, could be useful. And I'm gonna show you a video of very early days of this. And at the bottom, as you watch the video, I'm gonna tell you a little bit that in preliminary testing, this is a 10 or so individual with upper limb loss, translational amputation. And we did a very, very simple comparison of, doing this AMULA test, which is a validated test of performance with prosthetics, either with the existing prosthetic system or with the Soft10 Pro, which is the name of this prosthetic hand developed in Italy that uses the first principal component. And as you could see, the performance was for for one subject was the same, but for most subjects, or a couple of subjects was the same, or 2 or 3, but most subjects kind of improved. Now, what's really striking is not that it improved, it's the fact that the hand that they used for years, that the median of 8 years of practice, the practice of the Soft10 was just a few hours. And the reason why we think that was so effective is that it's very intuitive to use. You basically put one EMG electrode on the extensor, one on the flexors, and the difference between the two signals dictates whether the hand moves or not, and how strongly the hand moves. So it's very intuitive, unlike commercial prosthetic systems, which are much more sophisticated, more prone to break, et cetera, et cetera. So this is the latest model of the Soft10 Pro. As I mentioned, we started 2.5 years ago with a clinical trial funded by the NIH. 2 sites, ASU and the Mayo Clinic in Minnesota. And the design now is that we wanted to push the testing from the lab to the daily living kind of setting. And so what the subjects do, they come to the lab, they do a lab testing session, then they go home for 8 weeks. They wear the prosthetic system all day, or as many hours as they can, use the hand at least 50% of their waking time. every week straight, we download the data periodically, then we test it in the lab again. They do that with a soft hint, but they also do that after a break, 8 weeks with a commercial hint. And then we compare the two. The order is counterbalanced. So at the end of the 5 years, we hope to see, and the extent to which the soft hint really performs when pushed to the limits. I mean, some of the prosthetic users told us they changed the tire, which made me like, what? What did you do? Because I'm always afraid that the hint is gonna break, which occasionally might. But we hear, anecdotal stories that they're using it for all kind of stuff. So we're very happy to hear. But of course, we cannot look at the data yet because we need to wait for the end of the clinical trial. So 2.5 years from now, we should know whether this is as we hypothesize, could be a good alternative to commercial hand prosthesis. All right, so now let me switch gear a little bit, and now let me get to the human-human physical interaction. So physical interaction, when I started to read about it, it was kind of interesting because it poses a very different problem than controlling your own body. And I'm gonna get a little deeper in the next slide, but in general, physical interaction is pretty much ubiquitous, right? If you think about these examples, in the clinic, you could have the PT, as I mentioned earlier, kind of maneuvering your joints, your limbs, of course, dancing, moving objects from one room to another. So we have a lot of situations where you need to control your body in a way that your actions are coordinated in time and space with the action of somebody else, okay? Now, this is all great. And of course, during physical interaction, you can use a lot of sensory feedback, right? To guide what you're gonna do next. What's really, really cool is that what I told you before about when you control your own body makes tons of sense, right? You predict, you react, you learn, great. What do you do when you're gonna plan and execute with somebody else in the loop? So this works theoretically and experimentally very well if you control your own body. But now the problem is a little different, actually very different. Because now I cannot predict, I can predict when the object will be accelerated, but if you grab the top and if I grab the bottom, even if we have an external cue, your reaction time is different than mine. And even after we start accelerating, I still don't know exactly how much acceleration you're gonna give to it. So I'm gonna use my vision, I'm gonna use touch, I'm gonna use all of this online, and maybe use this to predict the next trial. But it's very, very different than just predicting the consequences of my motor commands on my own body. And this will really, I think, is really cool. So how do we do this? Clearly, we can move a table together with another person. And imagine you don't have verbal cues. You're using touch, you're using all kind of sound, you're using pretty much any cue you can to try to, again, anticipate and react, not just to your own body, on top of that, also to what the other person is doing. And it's this continuous loop, which is really sophisticated and really interesting. And again, in this particular case, I just gave the example, you only have forces as the information channel that allows you to predict and coordinate with somebody else. So what do we know? So despite the fact that for decades, motor control is focused on your ability to predict and control your own movements, in the last 10, 15 years, more and more groups have started to look at interactions, right? And I'd like to specify that I'm talking about physical interaction, but by no means that's the only type of interaction that we have, right? Think about an orchestra conductor. You have a bunch of musicians that are using visual cues of the conductor and sound from his or her own instrument and others, right? To somehow synchronize the motor action with all the others, right? So that's another type of interaction, even though there is no physical medium that binds the action, the physical action of everybody. And there's tons of really good work looking at hyperscanning, EEG, fMRI, when people interact. So it's really, really elegant work, really interesting, what makes two brains work in sync. When you look at physical interaction, you have another layer of complexity, and now you have some physical medium that transmits information from one to the other. And not all of that force is telling me something for me to use and decide what to do next. It's also just pure biomechanics of the object being moved back and forth. So the problem is to dissociate what's physical information with just physical interaction. So one of the things that came out of this literature, and this has been reviewed in a recent paper by Coleman et al., is that subjects use what they call a haptic channel, which is a channel of information that would arrive from touch. Okay, and that's what we use. There is also another problem that when you and I, let's say, lift an object together or move a table together, there is also in social interaction, that is when there is no physical medium, there is this concept of leader and follower. And the problem with that literature is that how you define leader and follower is very task specific. So for example, in one task, you could define the leader as the one that starts or that leads the movement in space or time. Fine. In other tasks, that might not work because the nature of the task is different. But one thing can be derived from this literature, both from social and physical interactions, is that the tasks assignment or the role assignment, I should say, the role that you take relative to another person is never perfectly symmetric. There is always some level of asymmetry, such that one might exert more force, one might lead in time, or one might lead in space. And so that's what this leader follower, kind of a general property, but we still don't understand exactly what makes somebody take the role of a leader or a follower. And this is what we looked at. I'm going to just show you very briefly two studies. One was done with a physical object, and the next study is going to be done on a virtual object. So for the physical object, we designed this device, which is a U-shaped object, and we put two manipulanda on the left and the right, the handles. Each handle is sensorized, as you can see here. You got a force torque sensor, and then we measure kind of biomechanical variables here. But the task is relatively simple. Imagine you and I are grasping this object together. There is a bubble level, and the task goal is to keep the object as level as possible. So if you see that the object is tilting, I should react to that tilt and try to correct for it, hoping that the other person is not going to do the same. And so there's kind of dialogue as you lift and hold. We tested a number of conditions, mostly looking at dyads, meaning pair to subject, dyadic conditions right here. I'm going to tell you the rationale in a moment. But we also did bimanual. And the reason why we wanted to do bimanual is that previous work I compared dyadic cooperation with the same subject from the dyadic cooperation as the control. The problem with that comparison is that if I do this stuff by myself or I do it with you, the biggest difference is that when I do it with you, you got two hands working on the object. So I have more degrees of freedom that could explain why. As reported in the literature, a subject which is not particularly good at doing this task is better when they work with somebody else. So it could be either because somehow I borrow from your skill and I get better at doing this with you, or because I have two effectors that might make the task more controllable, right? So because of that, we said, okay, we're gonna look at these dyadic conditions, but we also wanna do a control condition where each subject from the dyad also does the task by himself or herself. So that was the rationale why we went bimanual. And then we were also interested, because there is an issue of hand dominance, and in motor control, the idea is that the dominant limb is better at feed-forward control, at predicting what's going to happen to the object that you manipulate. The non-dominant limb for right-hand dominant subjects is better at feedback and static control. So we did these different configurations of the subject so that either both of them, one of them is dominant, one of them is non-dominant, and vice versa, or both of them use the dominant hand, or both of them use the non-dominant hand. An issue with doing this kind of pairing is that we're also changing whether they are looking at each other, like in a mirror, or not. And this actually turned out to be an interesting part of the story. Here's what the data looks like. So we measure the height of the object. So you do a static phase, then there's a sound, move it up, hold it, bring it down, hold it, and bring it down. And what we measure is the tilt, okay, because that's the error of the task. And we're asking them to minimize the error best they can. And then we take the maximum average value of this error as a kind of a summary measure of performance, okay, for each trial. We counterbalance the order, etc. So the nutshell, the paper is actually pretty long. The in the nutshell, so I'm putting the different combination of subjects to show you what these different color lines are. And this also takes a little bit to explain, but what we did was I do the task by myself, and then I do the task with somebody else. And then I compare whether my performance by myself is better or worse than the subject when he does it by himself that's gonna work with me as a diet, okay? So let's say me and Jason. Jason is of course much more skilled than me in this task than I am. So it will be given a positive score because it's got less tilt than I do. And so he's gonna be the better partner. He's gonna be here and I'm gonna be here. But then I'm gonna plot my performance when I work with him. And he's also his performance gonna be performed when he performs with me. And what happens is that for the subjects that are worse when they do the task by themselves, in this case me, when I work with Jason, my performance actually gets better, which has also been shown in the literature. When he works with me, his performance is slightly worse, okay? But there is no real trend. It doesn't get any worse as you look at, better partners on these axes. And so and as you could see on these different color lines with some noise here, but overall, this pattern is true regardless of the pairing, dominant and non-dominant hand, and whether I face my partner or the partner is side by side. So there are many reasons why the dominant and versus non-dominant pairing did not have any effect. And I can devote that to the question if you're interested in that. The better side by side than face to face is that possibly we hypothesize that it's got something to do with seeing a different kind of hand that you see it side by side. So this is almost as if you're working with another side of your body if it's side by side, whereas here you have a mirror image that might actually throw you off. You think about mirror neurons, for example. And this is also probably the most interesting part, that the worst performer can actually benefit from this dyadic combination. And we can rule out the fact that it's due to the using more degrees of freedom than not, because we have a control condition. Okay, so this takes care of the physical. And then I'm gonna tell you now about dyadic manipulation of a virtual object. Same rationale. Why would you use a virtual object here? What was wrong with the physical? There's nothing wrong, but the physical object is kind of limited when it comes to changing experimental conditions. So as I mentioned earlier, when we try to move a table out of this room, I can use the haptic feedback that I get from this vibration and the you pushing and pulling, and then I could use that information to make a decision. But if we were to leave this table and the table was compliant, the information you're transmitting me is not as veridical as if the table was rigid, right? I cannot change that on the fly with a physical object. I can change that with a virtual object. So this was a collaboration with Mitsuo Kawato in Japan, who once he saw what we were doing the physical object, he proposed to do collaboration using a robotic device. And that's what we did in Japan. So that this is his devices in his lab. So these are two robots and two subjects that are not cooperating. There's no visual feedback, no audio cues, no nothing, no verbal communication. And the task is similar to what I showed you before by Ivan, my PhD student. So imagine you have to move a beam, which is not physical, it's virtual, but you see a beam on the monitor. And you have to take it from your starting position to the end position here. And what the subject do not know is that the moment arm of this part of the beam is actually greater than this moment arm. There is a virtual pivot here. So this is the left subject, this is the right subject, there is a spring and stiffness, there's a spring and dashpot interaction forces here and here. So what we can do is to change the stiffness of the interaction from 0, where you can only use visual feedback to interact with the other subject. Or you could make it moderately stiff so that you get some information about the other subject, but not 100%. Or you could make it super rigid, so that now you get one-to-one veridical information about what the other person is doing. So we had 24 dyads. Again, they were not informed. To make the task engaging, we had temporal and spatial constraints, meaning that you couldn't, if you tilted more then plus or minus 1.5 degrees, you have to redo the trial. And so we count how many trials it takes you to get proficient. But you also need to finish it between 1 and 2 seconds. If you go too fast, it's not valid. If you do too slow, it's not valid. So, you know, it takes quite a while to get to the groove. So these are, I'm gonna just show you, I'm gonna focus on the highlights. So this is the high stiffness condition. And the color-coded traces show the transition from early trials to the hotter colors, which are the late trials. And this is the left handle position versus time. And this is the right handle position versus time. And what you see is that even though from a temporal perspective, they're going together, as they should, the left handle and the right handle, you see that there is this nice progression from early to late trials in a very orderly kind of fashion. So there is some evidence that they are co-adapting to each other, okay? So that's interesting because we didn't give any particular instructions about any rule of engagement. And when you have the low stiffness, sorry, this is the force. This is the left handle force, the right handle force. Again, very similar kind of pattern in terms of the colors and co-adaptation, not only in position, but also force. And then as you would expect, when there is no haptic feedback, when you only use vision, which is much slower than haptics and noisier, you see that there is no real pattern, neither in the position nor the force. So this is one diet, but already here you could see that, and of course this was replicated in other diets, you can see that there is some level of adaptation that engages both partners to do the task right. The other thing that we did was to model whether us giving this asymmetrical context kind of force the subject to act the way they did, meaning that one tends to lead, one tends to follow, as we'll see in a moment. And so the dotted line here indicates the space of feasible solution, meaning that you could have had the subject, the left hand will be here, relative to the right, or here. You could have done, in other words, you could have been leading or following, and you could have still done the task right. But what we see is that the left hand, the left minus the right handle difference in position, the left is always leading, okay? It's always on the top. And it gets more and more at the top as you get more experience. When there is no feedback, you explore the whole space. You can still do, these are all correct trials. This demonstration that you can still do the trial, but you're all over the place in terms of position, leading, following. And then when you compare the first with the last 5 trials, you see that there is more and more of an asymmetry in the difference in the position, because now this asymmetry, the left lead and the right is much greater for the high stiffness condition, and it's kind of blended together with the non-stiffness condition. And then just the passing time, which is also another metric. And this is also for the fourth. The fourth, interestingly, you see that the force, as you go to the last trials, it actually gets higher, okay, for the high stiffness. And a similar kind of trend is also seen here. Now, this by itself is telling us that you're not trying to minimize force. So force economy doesn't seem to be a key criterion here, because as you adapt in establishing a leader-follower relation, you don't seem to care about exerting more force than the other. And this is the last slide of the results, which is, kind of captures the key of the study. So what about performance? So we asked them to minimize the tilt angle of the beam, okay? And again, this is now showing the angle versus time from the start of the trials to the end. You see a very similar kind of color pattern, meaning that as you start off, the angle of the tilt is kind of high, still within the limits, but still high. But then you see that it approaches 0 as you get better and better and better. Even though it's not specifically required by the task. You could have settled at this and still do the task, okay? So the co-adaptation I showed you earlier seemed to be related to this better performance. And of course, when there is no haptic feedback, again, you do the task anyway, but the relationships are all over the place. And you see again, from the first 5 trials to the last 5 trials, that there's an improvement, like shown here. But here it is really what is interesting. When you relate the maximum degree of the beam tilt on the x-axis. You see it as you go from the right to the left, the different lines indicate the different kind of stiffness. If you just look at the blue, you see that you're going from early trials, which are the circle, to the crosses here. And you get, I'm sorry, the other way around. You go, no, that's correct. You go like this. And for the S400 condition, you basically get smaller and smaller, but you also get a greater difference in the position of the handle. So in other words, what I showed you, this is trying to relate two phenomena. One, the leader-follower relationship and the performance. And based on this, we conclude that the leader-follower relationship actually was instrumental in dictating this improvement in performance. And now I'm gonna shoot. Okay, I got 5 minutes. I'm gonna just spend this last 5 minutes just to give you an overview of why it is important to understand human-human interaction and how this could potentially be leveraged for designing human-machine interactions. So, and these are just some examples. So if you imagine having a machine now, imagine the task I showed you, but now instead of having another human partner, you have a robot. And, without imagining the sci-fi stories of a robot ripping your arm, which could have happened a few decades ago, given the technology of that time. But now the problem is, you need to have a controller for a robot that ideally should be able to predict what you're going to do next, either using EMG or subtle haptic cues, whatever the controller can use. But based on the architecture I showed you earlier, where two humans try to figure each other out and try to act accordingly, if you want a robot to look and behave like a human partner, then you should try to mimic as much as possible what you learn from the human-human interaction. That's one of the potential benefits of understanding human-human interactions. And then the other thing that is really important, and you see this all over the place, right? What subjects or patients might be wearing exoskeletons. So imagine these robots that you wear on your shoulders, on your hips, on your legs. And if you have a pathology, if you have a spinal cord lesion, if you have issues that impair your ability to control your body, this is where these robots could help to assist, right? But the problem is when you assist movement, again, you need to understand what I'm trying to do. Do I want to take a step? And how big is the step? And so the robot not only should not interfere, but ideally you want the robot to help you in doing what you meant to do, right? And so you should be able to do effective cooperation. And then ideally you should adapt. Now imagine you're trying to recover from an injury, right? So if you program the robot to do X, might be good this week, but next week, as I recover some of my function, the robot should be able to co-adapt, like what I showed you earlier in the leader-follower relationship, where the first trial is very different from the 40th trial, right? So all of this, again, are very, very ideal kind of objectives, very challenging to implement on a robot, both hardware and controller, okay? And these were a lot of labs are working on. And just to show you what I meant by exoskeleton, these are some examples of something you could have, kind of mounted on the floor. This could be for rehab often. This is workplace kind of assistance. Imagine having to lift, or in the military and the battlefield, imagine having to lift very heavy objects and your body clearly has a limit. Well, by also your body has a brain, and the robot might not have a brain as good as yours, right? So the ideal symbiotic relation is where you control the robot and the robot gives you augmented capabilities, yeah? So, but still, there needs to be a level of cooperation. Maybe not as sophisticated as the one I showed you experimented, but there's gotta be some kind of dialogue between the two. This is another example of exobionics, where now you wear this hardware. And again, this is a complement to what the subject can already do, maybe to some degree. And so here you see a therapist kind of assisting, but ideally, again, you want the system to interact with the subject. And this can also be whole body. So I'm sure you probably know the Locomat. It's been around for 20 years now. This was the very first robotic interface for rehabilitation of spinal cord patients in Zurich in Switzerland. It has undergone a lot of iterations and evolution, etc. But ultimately, these robots that you wear is partially assisted weight, and these robots can program gait cycles and can assist to different degrees depending on the level of the injury. This is a robot that we have in our lab. It's called M2 by Fourier Intelligence. It's a 2D kind of a robot where you can move, forward and sideways and combine. And this is mostly designed for stroke rehabilitation. It's a collaboration with the Barrow Neurological Institute. And then the cane arm, I already showed it to you, can be used, as a desktop kind of device. And I think I can conclude here. So I gave you an overview of how the symbiotic relation between robotics and neuroscience has evolved over the years and promises to deliver significant advances, both as research tool, but also as practical application to clinical and translational work. And then why understanding human-human interaction, besides being a very exciting conceptual kind of problem, a theoretical problem, can also have some very practical benefits when it comes to rehabilitation robotics, devices, whether wearable or not, for physical human performance augmentation and sensorimotor rehabilitation. And with that, this is, of course, my lab. I'm very grateful for the funding sources. These are the current collaborators. And this is the research team in my lab. Thank you.
Questions?
Yep. I got a question. With when you in the human to human interaction, does the worst performer do you feel uses more like kinesthetic information, like when that entrainment is going on, or more central signals to generate themselves become better?
So that's a great question. You're talking about what is the cause for the better performance?
Right, yes.
That is a fantastic question. I don't think anybody has really cracked that. The idea would be, but there is a way to look at that, and it's that there is some evidence in different tasks that it is as if you are allocating the main goals of the task into different buckets. And so that now, if you're by yourself, pretty much in charge of everything, of the timing, of the stiffness and the precision, right? If you're with somebody else, in particular somebody else who's better, you might be, from a cognitive workload, for example, you might be asked to do a little less from the perspective of attentional demands, because there's somebody that's kind of, I wouldn't say making up, but is clearly more skilled, because when he or she did it by himself or herself, was better able to use those cues effectively. So that's one way of kind of interpreting why dyadic might give you, as the worst performer, an edge, or might make you a little better.
Interesting.
Gary, is there anything on chat? I have a couple for. No, go ahead.
Actually, go.
Minor tangential.
No, fine, please.
Okay, all right, so I have a question about how the people who are interacting with these robotic interfaces, do you have a sense for how comfortable they feel with those interactions, and whether that might, like, their degree of comfort might have any relationship to sort of their improvement over time
So this is for patients that were.
for the patients, yeah.
So I don't have any personal experience with patients wearing exoskeletons, so I don't really know. I know, my only personal experience is with the prosthetics, right? And so if we look at prosthetics, there's quite a bit of literature that describe, on one hand, the high rate of abandonment of prosthetics, which again related to multiple factors. And then there's a lot of literature looking at what can you do to improve the sense of embodiment. And those two things are very much intermingled, because if you develop a sense of embodiment, meaning that the prosthetic feels like an extension of your body after repeated use and feedback, possibly it's more likely gonna stick to it. Abandonment is mostly due to the fact that particularly the hands, it's very difficult to mimic what a human hand can do. And so, and we, in the field in general, especially in the lab, we tend to build the ultimate engineering marvel. And then very often we don't ask the patient what they need it for. And so you give them this beautiful thing, which might not be able to do things that the patient cared for. And because it's complex, expensive, or is very prone to breaking, very heavy. So all of this compound, and at the end, basically the subject says, you know what, I use my intact hand. You know, I don't need to do this, it doesn't give me what I need to do, right? So I know that in the domain of it's wearable in a sense, but not, it's better than that, I think.
Yeah, no, I asked a question because I'm a behavioral and affective scientist and I'm interested in sort of how people's like perceptions and feelings of things will like impact
Yeah.
their engagement.
Yeah,
So,
so
yeah.
it's very fascinating, it's very complex at the same time, because, you know, if you could crack the problem of embodiment, right? And then you need to ask yourself, what are the fundamental ingredients that would improve the sense of embodiment? Is it the visual appearance? So would I ever feel a sense of embodiment wearing a hook? Which paradoxically, a lot of prosthetic users love. Aesthetically is not great, but get around doing some fundamental things in activities of daily living. But then at the same time, you might never get to sense of embodiment if you look at your your forearm attached to a hook. And then at the other end of the spectrum, you can get something that looks exactly, skin tone gloves. And the shape and everything looks like a real hand. And you really need to stare to see it's not a real hand. But it might not move the way you want it. So, to hit the right trade-off is not easy, right? And also has to respond in a way that's similar to the human hand. So I think if we could get to that point, then engineering could follow and say, okay, these are the features, could be aesthetics, could be, the way the hand moves, the way the hand feels. And then I didn't mention at all the fact that none, with exception of one recently introduced hand, none of these commercial hands have sensory feedback, none.
Interesting.
So in the next clinical trial, if we get to that, we want to look at the system that provides feedback, pressure feedback to the socket as a proxy to the contact force. But again, even that, it's a question mark, it's an open question. Would that be, because it's artificial feedback, would that be burdened cognitively? Or would they feel as if it allows them to get a better sense of what I'm doing?
Yeah.
So to be kind of investigated.
Thank you.
That's a good question. So the question is, if you looked at the diet performance over time between good solo performance and bad, I'm wondering if good performance have more solidified performance and thus they configure themselves as quickly to that performance. That's a great question. The question is whether if I understood correctly, if you get the worst performer to practice more, whether that could approach the level of an expert performer. I think that was the question. And that's a fantastic question. And we're looking at right now with the master student, we're looking at the effect of skill and expertise. So we're getting diets that perform, say, 3 to 4 times more trials. So they could be the experts, and then we're gonna put them and pair them with novice performance and look at the time course of that adaptation, where they could push them to become better performers, and then look at the time course of that performance over time. So that's a very, really good question. Your questions or?
My questions are totally off topic, so I'm gonna leave them until after we're finished.
You got a little excited, you probably.
I promise I was listening. Okay, I'll give you one. I promise I was listening to the rest of it, but I got stuck in the beginning of it, thinking of application.
Okay.
So I had a PhD student back in Sydney that he, for 20 years, worked with winter sports and mogul skiing in particular. And he was very interested in this idea of how you respond to different moguls. there's certain athletes that tend to be at the top of the podium all the time. And so he had so you kind of, you talked about the theoretical
Yeah,
versus the application, right? So I struggled because the timing of their responses to adjust their feet on the mogul was faster than the theoretical
yeah, the
sensory
loop,
response, yeah, so
So
where were you when we were trying to
That's
answer this question?
no, just, so that's it. To be super honest, to this day, when I look at this diagram, for all the beauty and
Yeah,
the fact that it can definitely account for a lot of experimental evidence. My biggest question is, this is good here as a static, kind of a snapshot. But in real time, it implies that every millisecond, every 10 millisecond, every 30, I don't know what the time course of this comparison is. And again, if it is one single discrete thing, it makes sense. But if you're looking at the movement that evolves over, I don't know, 3, 4, 5 seconds, I don't know exactly how these two things unfold, meaning the prediction and reaction. And there are some techniques, we use some of these techniques to see the time course of predicting and reacting, but even there, you have to make some assumptions about what prediction and reaction look like in your data.
It's interesting because they also, they're looking 2 to 3 moguls ahead. So there's some sort of processing that's going on with the mogul. I mean, you're talking milliseconds, right?
Yeah.
When they're adjusting, and then when there's still an adjustment though, that when they've already somehow processed that information of the mogul and they've moved on.
Yeah.
But then when they hit it, then there's also some sort of subtle adjustment too going on. So
Yeah.
it was so fast though that we
So, yeah,
get theoretical.
somebody has proposed in the group in Sweden that worked a lot on grasping manipulation and sensory afference, is that even though theoretically you have this constant stream of information coming from the environment, from your own body as it interacts with the environment, that doesn't mean that you're paying attention or you're using every millisecond of the information. In fact, theoretically, it kind of makes sense when I use common sense that as I grasp and manipulate an object, or as I strike the ground and do a jump or whatever, it makes a lot of sense that you should pay particular attention to the transitions that are behaviorally critical, rather than having this readout and then try to pick afterwards the thing that matter, right? So for me, for the grasping example, the most critically important transition is from when the hands stop moving and when the hands start accelerating the object. And this is where you see, from a sensory perspective, this is where you see some particular touch afferent fire like crazy in that transition. So it's possible that for prosthetics, you don't need to have this constant feedback telling the subject what they're doing. You might want, and some people are implementing that, by the way, in prosthetics. You might want something that tells you impact. Because once you know the impact, once you know that you're on the object, then you can deliver the motor commencement with it, right? So that's another compromise where this could work as long as you don't need to do this every millisecond.
Yeah.
Not that you couldn't, but just it's tough to really understand how that will work at such a high sampling rate.
Yeah.
At least for me,
Yep, we're out of time. All right, thank you very much again, and.
this, toward the end.
Oh, yeah, good.
Oh, you wrote it.
Is there, there's not, speaker DVD, DVD for next week, right?
TBD.
There we go, right, cool. Yes, no longer the 29th, we're not doing Bill O'Reilly. But it's TBD, so thanks a lot again, appreciate it, Marco.
My pleasure.
And, see you next week.
All right.
Great.
Thank you.